In this video, I'm just going to give a quick overview of what's called the direct product. And sometimes you'll see it called the outer product, but I'll be using the term direct product here. And so we saw in in a few previous videos that the direct sum gives us this, where we just sort of stack everything in the diagonals of a matrix. But the direct product instead, so if we have A times B, so the direct product of A and B. So we go through all of the B's in this upper left up here, multiplied by the A11. Then we do all of the B's in this upper right, multiplied by the A12, and so on and so forth, so that we have in the upper left A11, B11, A11, B12, A11, B21, A11, B22, and so on and so forth. And so for our groups in general, we have the D alpha beta here representation of our group equaling the direct product of the alpha and the beta representations here. And so we can use the following two representations here. So we have this one that we've been using, and then we have this this non-unitary basis here that we've seen in a few other videos as well. So the direct product for each of these, so I just kind of went through into the direct product for each of them. So obviously the identity is just going to have ones down the diagonal here, because 1 times 1, 0 times 1, 0 times 1, 1 times 1. And so you just go through that through the whole thing. So with the rotation, we end up getting something that looks like this. So we have this big 4 by 4 matrix. So we see that when we take a 2 by 2 and a 2 by 2, we end up with a 4 by 4. So the dimensions of it will be the multiplication of the dimensions of the two representations that we are using. And so we can go through with each of these, and so we end up with this new representation here. So I have the D3 times 4 down here, and so we have these 4 by 4 matrices here. And so we can get the characters of them. So the character of the identity is just adding down the diagonal, so that's 4. The C3 and the C3 inverse are 1, because we have 0, half, 0, and half, half, 0, half, 0. And then these reflections, we get 0. And so in general, the character of the new representation is just the character of the first one times the character of the second one. And that should make sense because our C3V, remember, we have in our E column, we have a 2. Our two C3s are 1, because 1 times 1 is 1. And then 0 times 0 is 0 for these. And so the C3 classes, remember, we had a 1. And then the sigma classes, we had the zeros there. So we can actually look at that here. So we have the 2 times 2 equals 4, and so on. So the direct product also has the property that if we take the matrix multiplication of two elements here of our group and do the direct product with the matrix multiplication of two other elements of the group, that equals the direct product of these first two elements of our group, which will make another matrix of higher order. And then we do a matrix multiplication with the B and D here, with the direct product of B and D here, which will be another matrix of that same order as the direct product of A and C. So the matrix multiplication of AB produces another matrix representation in the group, as does the matrix multiplication CD. The direct product of these two matrices then gives the same matrix as if we took the matrix multiplication of the direct product of AC and then BD. And so if we have our A equals R alpha, B equals S alpha, C equals R beta, D equals S beta, and our group has that R S equals T, that the when we do the S and then the R symmetry operations, that's the same as some other operation in our group here, such that the matrix representation of R and S is equal to the matrix representation of T in our alpha representation, and same in our beta representation. We then see that if we do the direct product of the R and the alpha representation of the R and the beta representation, and do the matrix multiplication of the S and the alpha representation and the S and the beta representation. That's the same as doing the R alpha S alpha, which we have up here, and the R beta S beta, which we have up here, which is just the same as doing the direct product of the T alpha and T beta. So the direct products have the same multiplication table as the group elements. So more generally, if we have a G alpha dimensional vector space V alpha and a G beta dimensional vector space V beta, each spanned by these basis vectors here going from 1 to G alpha and 1 to G beta. And these carry representations D alpha and D beta respectively of our same group here, G. So they're both representations of the same group, G. So those representations in each vector space are mapped like this. Then the direct product is then the basis vector pairs like this. So we are interpreting these commutatively so that we're not counting things multiple times. And so we get this much longer list, this much larger set of basis vectors here that are sort of the direct products or the products of each of these basis vectors here. And so kind of going through all the permutations of I and J. So this direct product can be used, for example, in getting the symmetry of the overall wave function for all the electrons in an atom. And so the overall wave function of a system of particles is the direct product of those particles. So if we have the wave functions, this psi1, where we have x1, y1, z1, and the psi2, x2, y2, z2, then two non-interacting electrons in the atom can be described with these four products here. So we just permutate the ones and twos through all of these. And so the three function spaces are then, so this is just for the one particle, this is just for the one other particle, then this other one is for the system of both particles, where the psi ij is equal to the product of the psi I alpha and psi j beta here, is the direct product of the functions. They make up a basis in function space. And so a rotation of phi in either one of these spaces is just going to be a rotation of our psi here is this rotation matrix. So it's the cosine, minus sine, sine, and cosine here. And that will be the same for both of these spaces here. And a rotation in the direct product space is done with a matrix that is the direct product of the rotation matrices. So we take the direct product of these rotation matrices and we end up with a matrix that looks like this. And so we can test, if we take the trace of each of these individual matrices, so the character of them will be 2 cosine phi and 2 cosine phi, and then as we said above, the character of this new one should be the product of both of those characters, and it in fact is. So we have 1, 2, 3, 4 cosine squared, so it's 4 cosine squared of phi. And so making a rotation in this direct product space, so we're doing a rotation of the direct product space, we'll use this 4x4 matrix now on this 4-dimensional vector here. And so that will send each of these functions into these linear combinations of each of the functions, because we are rotating the functions in the function space. But anyway, that, as I said, is what the direct product is, which is important in chemistry and quantum mechanics and things like that. And so that's why I use that sort of quantum mechanical example. But anyway, I hope you found this video helpful, and I will see you in the next one.